In this video, we will continue discussing finding areas enclosed by polar curves. So recall the basic formula. If we have a polar curve represented by a function r equals f of theta, and we want to know the area enclosed between theta values alpha and beta, what that is going to create is this almost pizza slice region whose area is given by the formula. 1/2 the integral over how those theta values vary, and what we integrate is, I'll say, r squared. So let's look at another very common example. Let's find the area of the region enclosed by one loop of the polar curve r equals sine of 3 theta. So for an example like this, you don't actually need to sketch the entire polar curve to see what your limits of integration should be, but it certainly could help. If you go through the process we discussed earlier, you can find that r equals sine 3 theta is a curve given here. We might refer to this as being a 3-petaled flower. And we want to essentially find what is the area enclosed by one of these loops or one of these petals. And in terms of theta values, thinking about where sine will be equal to 0, 0, pi, 2 pi, when you plug in 0, you get 0. So giving this first point. And then this first petal is traced out as you go from 0 to pi over 3, because 3 times pi over 3 is pi. So the enclosed area that we are looking for is going to be 1/2 the definite integral over how those theta values vary. So one loop or one flower petal will be 0 to pi over 3. And what we need to integrate is sine of 3 theta squared. So let's evaluate this integral. Now, once again, to evaluate this integral, it's useful and necessary to recall this double angle formula from cosine. Sine squared of something, so in this case, r something is going to be this 3 theta, is equal to 1/2 1 minus cosine of 2 times that something. So letting the 1/2 pull out front, we'll have 1/2 times 1/2 is 1/4. We're integrating from 0 to pi over 3, and we are going to have 1 minus cosine of 2 times something, but remember our something, this 3 theta, is what's getting plugged in. So 2 times 3 theta is 6 theta. Then we go ahead and just anti-differentiate term by term. So the antiderivative of 1 with respect to theta is theta. And for cosine 6 theta, that would be minus 1/6 sine of 6 theta. And note, if you don't immediately recognize what that antiderivative of cosine of 6 theta will be, you could always use a substitution. Your substitution would be u equals 6 theta. And you can also double check this very easily with a differentiation. When you differentiate, the chain rule tells you it would be cosine 6 theta times 6, which cancels off that 1/6 out front. So we plug in pi over 3, we put a minus sign, and we plug in 0. And notice when you plug in pi over 3, 6 times pi over 3 is 2 pi. Sine of 2 pi is 0. Sine of 0 is 0. And when theta is 0, you get 0. So the only thing that you get that would be non-zero is when pi over 3 is plugged in for theta. So it's pi over 3 minus 0, minus 0, minus 0, just to see everything. So the area of one loop is pi over 12. Now note, alternatively, one also could have integrated from 0 to 2 pi and then divided your answer by 3, because the graph of r equals sine 3 theta has 3 petals.